Hello and welcome to my talk on first-order model checking in random graphs and complex networks. I'm Jan Dreyer, and this is joint work with Philipp Kuinke and Peter Rosmanit. Our work is motivated by the study of complex networks. They're all around us, for example in the form of social networks, computer networks, or biological networks, and we want to analyze what kind of problems we can and cannot solve efficiently on such networks. Ideally, we would like to show that problems that are proven to be hard in theory can nevertheless be solved efficiently on complex networks. However, we need to formalize what we mean by complex networks in order to rigorously study this question. Luckily, the field of network science has been a very active field of research over the last 20 years. Network scientists try to understand the behavior of complex networks. They found out that all these different networks actually have a lot in common and formulated mathematical models of these networks. They noticed that randomness is an excellent way to capture their seemingly chaotic structure, and they came up with many different random graph models such as the preferential attachment model, the hyperbolic random graph model, and others. These mathematical models now give us the necessary formalism to make our search for efficient algorithms on complex networks rigorous. In this paper we present algorithms that, when given an input sampled from a random graph model, are provably fast. This means that their expected runtime is bounded. We defined the new notion of a-power-law-boundedness and show that all problems expressible in first-order logic can be solved in expected linear time on power-law-bounded random graph models. We also show that many of the well-established models of complex networks are power-law-bounded. We hope that this contributes to the question of which problems are tractable on complex networks in principle. We obtain a quite general result, but it comes with the usual drawbacks of such results. It has huge hidden constants which make it, in its current form, impossible to implement. So significant engineering challenges would need to be overcome to turn these results into practically useful algorithms. Earlier we said that we want to find efficient algorithms for all problems expressible in first-order logic. Let us sketch what kind of problems these are. In first-order logic, you can quantify over vertices and ask whether they're adjacent or equal. A graph has an independent set of size k if there are k vertices which are pairwise not equal and non-adjacent. Similarly, a graph has a dominating set of size k if there are k vertices such that all vertices y are either adjacent to one of the k vertices or equal to one of the k vertices. Note that you can trivially solve these problems in time n to the o of k, but according to ETH, this running time is essentially optimal. Instead of having a separate algorithm for k independent set, k dominating set, and so forth, we can write these problems down as logical formulas and instead have a generic algorithm which evaluates these formulas. This problem is known as the model checking problem. It gets as input a graph G and a logical sentence phi, and the problem is to decide whether phi is true in the graph or not. Ideally, we would like to solve this problem in some function of the formula length times n, the size of the graph. If we're successful, then for some constant value of k, the length of the representative formula is constant and f of phi is also constant, leading to a linear time algorithm for k independent set, k dominating set, and similar problems. Courcell's theorem states that MSO model checking on bounded tree-width graph classes is FPT. Over the years, first-order model checking has been proven to be tractable in more and more general sparse graph classes. Most notably, one can solve the problem in FPT time on nowhere dense graph classes. This is optimal in the sense that a graph class is somewhere dense if and only if it is not nowhere dense, and on subgraph closed somewhere dense graph classes, first-order model checking is as hard as on general graphs. Let us now talk about the networks that we see in the real world and the kind of properties they have in common. Many resources are very unevenly distributed. For example, most people have a little bit of money, but there's a few people who hold large amounts of it. The same can be said about the degree distribution in complex networks. They often resemble a power law distribution, meaning that the fraction of vertices with degree k is proportional to k to the minus alpha, where alpha has been empirically shown to be somewhere between 2 and 3 usually. Furthermore, complex networks tend to have clusters, like those dense regions here on the graph on the left. Also, there's a so-called small world property, which states that everyone is only a few hops away from anybody else in the network. There exist many models of complex networks which try to imitate those features. We call them random graph models, and formally they're probability distributions over graphs. Previously, people have analyzed how those random graph models relate to our hierarchy of sparse graph classes. Some models have been shown to have bounded expansion in the limit, meaning that the algorithmic techniques for bounded expansion graph classes are also applicable to these models. Others are shown to be somewhere dense, which means that we have to try something else for these models. With all this in place, we can now present our results. We say a random graph model is 3-power-law bounded if it more or less satisfies the following conditions. First of all, the fraction of vertices with degree k should be roughly k to the minus 3. In real networks, we typically observe k to the minus alpha, where alpha is between 2 and 3. So this condition is at the edge of what you would still observe in real networks. And the second condition is that 3-power-law bounded networks need to be unclustered. This is in contradiction to what you would usually observe. Real networks tend to be clustered. And our result is now the following. We show that when you're given a first-order sentence phi and a graph G sampled from a 3-power-law bounded random graph model, that one can decide whether phi is true on G in expected time some function of the length of phi times n to the 1 plus epsilon, where epsilon can be chosen arbitrarily small. This means we solve the first-order model checking problem on 3-power-law bounded random graph models in FPT time. Now you may ask yourself two questions. First of all, what if in the first condition alpha is not 3 but some smaller number? Can you still solve the model checking problem efficiently? And here the answer is more likely to be no. Under some reasonable assumptions, we show that the problem becomes hard under these circumstances. And the second question is, what about clustered graphs? And here we don't know. The big open question is whether we can solve the model checking problem on clustered random graph models. And if you're interested in working on this with us, please contact us. Let me next explain to you which kind of networks are 3-power-law bounded. The first example would be the preferential attachment model. It has been introduced by Barabasi and Albert in 1999 to explain the structure of the World Wide Web. It's an evolutionary graph model which works as follows. We start with a single node, then we always insert one new vertex with a constant number of edges from the new vertex to the rest of the graph. In this example, it's 2 new edges per vertex. And the probability that an edge is attached to a target vertex is proportional to the degree of the target vertex at the time. This effect has been called the rich get richer, because if a vertex already has a high degree, then the probability that it continues to attract more and more edges is higher. And in fact, you can show that after n vertices have been inserted, the expected degree of the ith vertex is approximately square root of n over I. This is similar to what you would observe in real-world networks. That's why the preferential attachment model is considered a nice explanation of why real-world networks have the kind of degree distribution that they have. But there are other, more direct ways to get a similar degree distribution. For example, the Chung-Lu model. Here you start with n vertices, and you say you attach the ith and the jth vertex with a probability of 1 over square root of I times j. This means that for the first vertices, they're attached with a more or less constant probability, and for the last vertices, they're attached with a probability of roughly 1 over n. All edges are added independently. Our notion of 3-power-law boundedness can be considered as a generalization of this model, where edges can be moderately dependent with each other. A random graph model with vertices 1 to n is 3-power-law bounded if the probability that some subset of the edges, E, is present in the graph is bounded by some term. Let's break down this term. This inner term, 1 over square root of I times j, is simply the probability of an edge between vertex I and j in the Chung-Lu model. If two events are independent, then the probability of both events occurring together is simply the product of both individual probabilities. And since in the Chung-Lu model edges are independent, then this product term here would be the probability that all edges in E are present in the graph. Earlier I said that 3-power-law boundedness is a generalization of the Chung-Lu model, and this is realized by this term here. The probability of an edge set E can be a factor log n to the O of E squared larger than what you would expect in a Chung-Lu model. This logarithmic term acts as some kind of slag that allows edges to be moderately dependent. We already discussed that the preferential attachment model is 3-power law bounded. The Chung-Lu model also fits into our framework for certain parameter values. Also the Erdős-Rényi model and the configuration model. On the other hand, there are some random graph models which do not fit in our framework, mostly because they are clustered. For example, the hyperbolic random graph model or the random intersection model. And this is because clustering needs a strong dependence between edges. And this logarithmic term is not large enough to capture the strong dependence between edges needed for clustering. Now that we talked about which random graph models are 3-power law dominated, let us talk about their asymptotic structure. Asymptotic structure means the following. If we sample a graph with n vertices from a 3-power law dominated random graph model, as n approaches infinity, we observe the following structure with probability 1. We fix any vertex and induce the graph on all vertices with distance at most r from it. First of all, there are log n to the O of r squared many vertices, which we call the core of the neighborhood. To this small core, a number of even smaller subgraphs are attached. We call these subgraphs protrusions. Each protrusion has O of r vertices. We only draw 5 protrusions here, but there can actually be a large number of them. Each protrusion is only weakly connected to the core. There are only a constant number of edges from each protrusion to the core. And at last, there are trees connected to the core and to the protrusions. Each tree is connected to the remaining graph by exactly one edge. So the structural complexity of such an induced neighborhood clearly lies in the core, but the rest of the graph is well separated from the core, and the size of the core is only polylogarithmic in n. So neighborhoods in 3-power law dominated random graphs have this algorithmically interesting structure in the limit, and it would be interesting to empirically analyze to what extent real networks really have such a structure. Let us next describe how our model checking algorithm works. The algorithm gets as input a random graph sampled from a 3-power law bounded random graph model. This input may look something like this. The first thing we do is we use Geifmann's localities theorem. This theorem states that we can replace a first order formula with an equivalent formula which makes only statements about local regions. So from now on, we only need to consider local regions or neighborhoods of our random graph. As discussed earlier, these neighborhoods consist of a core to which protrusions and trees are attached. So we know that it's very likely that there is a small core, but we still need to find it. Turns out that it's not so easy to find the smallest core possible, so instead we find a core which is a little bit larger. Once we have the core, we can also identify the attached protrusions and trees. As a next step, we prune them. We do so using a result from finite model theory by Pfifferman and Vaught. It states that it's okay to replace a large tree or collection of protrusions with something much smaller, as long as the smaller graph satisfies exactly the same short first-order formulas as the original tree or protrusion. After pruning, the resulting graph is small enough that we can directly run the naive model-checking brute force algorithm on it. We do so for every neighborhood of the graph. Next, we analyze the expected runtime of this algorithm. At first, we have some polynomial factors, for example, for iterating over every neighborhood. Next, we make a case distinction on the size of the kernel. So we multiply the probability that the kernel has size x with the runtime, assuming that the kernel has a size x. And if the kernel has size x, then we basically prune away everything except for the kernel of size roughly x. On this we run the brute force model checking algorithm, which has then a running time of x to the length of the formula. And in order to get our desired running time, we need to bound the probability that the kernel is greater than x for every x. In particular, we want that the probability of this is roughly the inverse of this, because then they cancel each other out and the whole sum does not grow too bad. So let me describe how we bound the probability that the core is large. This is the most complicated part of the paper, though I can only sketch it briefly. So at first we assume that the core is large somewhere in the graph. Then, after many pages of proofs, we show that this implies that there exists some edge set E from a collection pi of blocking sets, such that all edges in E are present in our graph. And 3-power-law boundedness was defined exactly in the way that for some fixed set E, we get a nice bound on the probability that all edges in E are present in the graph. But since we don't know which blocking set is present in the graph, we use a union bound. It tells us that the probability that any blocking set from pi is present in the graph is bounded by the following term. We sum over all edge sets E in pi and then take the probability that E is present in the graph. We substitute the bound from above and then obtain a bound on the probability that the core is large. Using some further calculations, we can then show that this probability is bounded in just the right way, that the running time of our algorithm is as desired. And that concludes my talk. In summary, we've solved the first-order model checking problem on 3-power-law bounded random graph models. These are those where the fraction of vertices with degree k is roughly k to the minus 3, and which are generally unclustered. The big open question is whether we can also solve the model checking problem on clustered graphs. Thanks for watching, and if you have any questions, feel free to reach out to me.